Hello, good day everyone to the showcase run by SES, the satellite company based in Luxembourg. We are very excited to share with you today our latest developments, which shows how SES is actually innovating in terms of communications by satellite, essentially. We have today three distinguished speakers who will talk about our multi-constellation system. We'll talk about our antennas on the ground and also our encryption systems with quantum technology. So Stewart Sanders will be our first speaker. He's Executive Vice President in SES. He's in charge of our A3B Empire system, our new constellation, very powerful constellation of satellites. We will then have Brian Billman from Isotropic Systems. Isotropic is a manufacturer of antennas, and he will explain how the new generation of satellite antenna can actually look at different orbital positions and enable to work with different systems, since SES is the only commercial operator of satellite in the world running different orbital positions. And we will then finish with Thierry Draus, also from SES TechCom, more specifically. Thierry will talk about quantum, how quantum is a reality for SES, and very soon a reality for our satellite system. Very important for the security of our communication networks. Are you ready to go? So now I'm going the floor to Stewart, who will talk about the advantage of SES having multi-orbit constellations. Stewart.
Okay, good morning, everybody. Hopefully you can see the first slide up there. I'm just going to briefly talk about A3B Empire and explain to you that it's a lot more than just next generation satellites. As Cecil said, I am responsible for the development, implementation of the A3B Empire system, soup to nuts, as they say in the US. Pretty much everything except the actual satellite build. We've got teams that focus very much on that. But what we're bringing here is not just satellites. It is about an infrastructure and a number of components, some of which the other speakers will talk about. So next slide, please. Given this is a Spectrum conference, I thought it'd be interesting to show this. This is actually a snapshot from an animation that was produced in partnership with MIT. And we've got them doing some work around large data set correlation, but also to look at algorithms for some of the resource management. And what you're seeing here is a color-coded spectrum reuse map for the A3B Empire satellites. And this, it's too difficult, too heavy to show it over the webinar, but I just snapshot it. What you would see is this progression of the satellites and the beams rotating as the satellites progress, but still always maintaining each customer at the center of the beam. That's the beauty of the electronically steered phased array that we have on the satellites, and the underlying management of that system by the resource management engine, which I'll talk about a little bit more. Something that we're developing with a partner. This is not stuff you can buy off the shelf. So right there's a high level of innovation. Next slide, please. So this is a little bit busy, but in the interest of keeping the number of slides down, I thought I'd try and put a little bit more into the slides. So top right, you see the ARC, the Adaptive Resource Controller, as we're calling it, which is an acronym that comes up nicely into ARC, but really it's a software engine that allows us to manage the space segment in concert with the ground segment. And what I said before is very much true. What we're delivering here is not just initially 6 satellites growing to 11 satellite constellation, which we can keep growing. It's very much about the overall infrastructure and how that space segment integrates with the ground segment. The satellites themselves, as you see in top middle, are quite different than anything you will have seen before. If you've been up close to a geo satellite, you'll know they are big. They have lots of appendages, lots of antennas hanging off. We're really bringing to market the next generation of technology in satellite in the commercial world. And we are the only MEO commercial operator, and therefore by definition we're the only MEO geo operator. And we really believe in the benefit of that hybrid orbit domain strategy. The value that one orbit brings versus another, we can bring both of those values to the customer through flexible ground infrastructure, and where it makes sense, allowing the customers to roam from one to the other, if it's a mobility solution, for instance, whether aero or maritime, but also to allow data to move across the overall infrastructure according to its need. As if it needs low latency, it can go through a low latency path. If it needs reach, it can go through a geo. We will augment over time to increase the coverage of the MEO system. But the satellites themselves, fully digitized payload and full electronic beamforming. So as you can see, they are basically just look like boxes, roughly 2 meters by 2 meters by 1. So they're not very big, so we can get 4 of them on a Falcon 9. And while they aren't particularly interesting to look at, let's say, compared to other satellites, they have a huge capability. Full beamforming, you can generate anywhere from 1 beam to 5,000 beams per satellite, and full spectrum reuse, multiple spectrum reuse, so that we get an awful lot of throughput. At the bottom, open standard integration. We're leveraging open standards used in the terrestrial world to make the satellite environment look like the terrestrial world. We're already the first, and I still think the only MEF standard certified satellite operator over our existing MEO system. And what that means is the customer can buy in and they know they're going to get a certain standard of carrier grade data transition across the networks because of the standards we're using. And that opens up a lot of interesting possibilities. We're not into proprietary standards. We're not into making it difficult to work with us. We want to make it as easy as possible. Security comes on top of that. It's not done by making yourself difficult to work with. It comes on top of that. The multi-beam electronically steered antennas, I'll defer to Brian, who's going to talk in much more detail, but this is a really exciting addition too. We are not going to use solely ESAs. We will certainly use parabolic antennas, but it is an interesting part of the overall infrastructure. And the beamforming, both at the terrestrial level with these kind of antennas, but also at spacecraft level, opens up a whole load of interesting opportunities and services that you can offer to customers in terms of, particularly for government customers, resiliency against accidental or more likely deliberate jamming, for instance. Flyaway gateways. We are not limited on the number of gateways that we can deliver on this system, and we want to offer customers the ability to have fast deploy gateways as they need them. And there's obviously a particular segment that's going to be interested in that kind of thing. And that is something we've already completed the first commercial deal around that kind of gateway, and I certainly expect more of those things to come. And then cloud partnering. We've made a lot of public statements about our relationship with Microsoft. We believe that the reason that companies like Microsoft are interested in space operators is because of the reach and capability that we provide that they cannot get elsewhere. And it's a really good symbiotic relationship. It goes much more beyond just satellite connectivity. There's a whole bunch of other stuff that we're giving, both providing for them and then providing for us. And a lot of the software systems that we're going to be used to underlie this system will be cloud-based. And then lastly, just because of all of these pieces, many of which are innovative and coming to the market for the first time, the combination opens up a lot of new service opportunities for our customers, but we can couple that with the necessary security. And we think we've got game-changing capability, fully differentiated capability, in fact, for ISRs in particular, as an example. Because of the flexibility on the forward to return ratio, we don't have constraints on that. And most data services are forward dominant, but there are some notable exceptions which are return dominant, such as an ISR, if you can imagine that high definition camera producing a lot of data. And that's certainly something we can provide, and we can put that within a framework of all of the kind of security requirements those government end users need. So I'll stop there. It's a hugely rushed introduction to what we're doing, but just to contextualize it, and I hope you have a great conference. Thank you.
Thank you, Stewart. Very interesting. I hear a lot about how flexible this system is going to be, and I hear a lot about the fact that in terms of using resources, a scarce resource as spectrum, we will go to a completely different paradigm and make something which will use spectrum much more efficiently in a much more flexible way. I want to invite the audience really to pose any question in the chat. Don't be shy. Even the most basic questions. I know some of this presentation can sound and look quite technical, but I think they really bring a lot of information about spectrum usage of satellite systems. I'd like now to give the floor to Brian Billman without any further ado. Brian, please.
Yes, great. Thanks, Cecile. And hello, everyone. So again, my name is Brian Billman. I'm the head of product at Isotropic Systems. So today I'm going to share a little bit about our company, explain a bit about our transformational optics technology, and explain how we're using that technology to deliver a multi-link user terminal that will really unleash the full capabilities of SATCOM systems like SES Empire. So let me start real quickly by setting the scene with the industry. As many of us know, we are seeing new changes like lower launch cost and newer satellite technology, which has really led to this explosion of both capacity and capabilities in space. And so we're seeing this in the form of new satellites and new orbits, software-defined networks, cloud computing, all these innovations that actually Stuart just mentioned and the things we're going to be seeing on SES Empower. But on the ground, we're really stuck with using terminal technology mainly that was invented over 130 years ago. So, we're stuck with single link antennas that were built for this legacy geo world. And so at Isotropic, we're solving that kind of final missing link by developing the world's first multi-link, multi-orbit user terminal. And again, that's because no matter what other technology you talk about, whether it's parabolics, mechanical flat panels, or even other ESAs, they can all only support one connection to one satellite. And so that means that for NGSO constellations, 2 terminals would be required at every user site to provide the seamless make-before-break handover between rising and setting satellites. And since they're mechanically steered antennas, which means they have single points of failure, many times you would want to put a third antenna there for redundancy. And then, of course, you would also want a third antenna if you'd like to take advantage of other satellites and other orbits. And what we're doing is we are replacing all of that with a single, fully integrated terminal. So each Isotropic Systems terminal can establish multiple full performance links from a single electronically scanned antenna. And the key part here is that each link behaves exactly the same as if you had an additional antenna. So there is absolutely no reduction in performance as we turn on those additional links. So this really is true multi-beam because this is the combining of multiple full performance links into a single terminal. So that, of course, is great not only for the make-before-break handovers on NGSO constellations, but it also allows for multi-satellite, multi-orbit, and multi-service capabilities to a single terminal. And this is one of the ways why it's been really great working with SES because, as Stuart mentioned, they're the only operator with multi-orbit assets. And so we can fully leverage all of their satellites just from a single terminal. So I know a lot of that kind of sounds like magic because there's really been no other technology that can do that before, and it almost seems like it's breaking the laws of physics. So if we can please go to the next slide, I'd like to share a little bit just about how the technology works itself, which helps provide a little bit of context there. So it all starts with transformational optics. And so that means that for any given space or volume, what we do is we actually mathematically solve for what material properties are required to give us the radio performance we want within that space. And so what this device does here that you're seeing is it's actually focusing energy into a small area under this lens based on the direction of the satellite. And this is how we accomplish this revolutionary multi-beam capability because the energy from different satellites is getting funneled into different circuit chains. So that means that each link we create is using completely separate circuitry, but they're both using the full antenna aperture. And so a lot of the work that would typically require these expensive high-powered circuits, we've collapsed all of that into this kind of single, completely passive device. So it doesn't need power or control. And so from this device, every time we turn on a link, we're only using a fraction of the circuitry. And then when we want to create more of those links, we simply just turn on more of the circuits. So in the animation that you're seeing here, this is a single lens being used to create 3 full performance links to 3 satellites in 3 different directions simultaneously. If we move on to the next slide, please, I'll talk a little bit about how we take that technology and turn that into terminal products. So we house those together in what we call Trilens Modules, and so this includes the associated feeds that radiate under the lenses, and includes the circuitry that I mentioned that are under each lens. And this is the core building block of really every product that we build, because to create a terminal, we take multiple of these Trilens modules and we tile them together into a full array to create the full terminal. And so we can pick different numbers of modules, we can scale it up and down in size, we can pick different shapes and conform them to surfaces. And so really what this allows us to do is take the same core technology and create products that are specifically optimized for each market and for each customer. But we've taken that a little bit of a step further, because there's historically been another challenge in the industry, and that's complexity. So the fact that for many of these installations with these big single-link parabolics, you're going to require site surveys, civils, concrete pours, skilled installations. It can be fairly limiting for certain customers in certain markets. And so sometimes the installation costs can be prohibitively expensive. And then even when you're done with that, since they are kind of mechanically steered antennas, you'll need routine maintenance to upkeep function, especially because they have those single points of failure. So that's critically important, right? But since what we've done is we've collapsed all of that into this fully integrated single terminal solution. So what you're seeing here on the screen includes the functionality that would typically require bucks and LNBs and ACUs and power supplies and even modems that can all be housed within this terminal shown here. So that means you can take this out to any site, throw it on whatever surface is available, on top of the shed perhaps, turn it on, and we'll find the satellites automatically, and that's it. So now that I've kind of covered how the technology works a little bit, if we move on to the next slide, please, I can share just a little bit about where we are in terms of this product development. So it has definitely been a long road pioneering the field of science to get to where we are today. But I'm happy to say that most of this technology risk is actually behind us. So we've developed prototypes in both Ku and Ka frequency bands. We've fully characterized them in the chamber for things like PSD mask compliance. We've taken them out into the real world and we've tested them on both GEO and NGO, so satellites with over-the-air live links. And we've been incredibly fortunate, again, to work with the best in the industry like SES on this. And so right now we are in our final stages of preparing for a product launch, which will be next year in 2022. And to put a little more color on that, if we go on to the next slide, please, show you just some kind of pictures of where we are in some of our facilities, which are out in the UK. So we've recently opened up a state-of-the-art engineering and production facility so that we can rigorously test these terminals to meet the highest standards as we manufacture and launch these products next year. And also our team is growing very rapidly. So if we have any world-class engineers listening in today and you want to be a part of this exciting journey, please go ahead and check the jobs on our website. I know that was a lot quickly, so let me just kind of wrap it up and summarize on the next slide, please. So we are launching this terminal next year, and this is really going to be a seismic shift in the industry, because the multiple full performance beams that this terminal can create not only support make before break handovers, but allows multiple services from multiple satellites to be delivered to the user simultaneously. We're significantly simplifying the installation by collapsing all of this into a single fully integrated terminal, and we're offering out-of-the-box plug-and-play experience. But most importantly, as we see kind of these incredibly powerful new satellites and constellations like SES Empire, there's finally going to be a user terminal on the ground that can unlock the full potential of these systems. Again, feel free to pose any questions you have in the chat there. And then also after this session, you can reach me at this email address or on our website there. Thank you.
Thank you, Brian. very, very interesting, very exciting, actually, and super timely with the launch of our A3B Empire system next year. So I see it as quite revolutionary because so much has been said about, how heavy the installation of satellite antennas can be, especially if you start talking about different frequency bands or if you're talking about different constellations. But you seem to have now the magic solution that provides visibility to different orbits and also to different frequency bands. But maybe we can talk more about that in the question and answer session later on. So now I'd like to give the floor to Thierry from SES TechCom. He will talk about quantum and why and how quantum is so essential to us to improve security over satellite networks. Thierry.
Thank you, Cécile. Hello, everyone. So I'm gonna present you today an innovative project we are currently developing at SES called the Space-Based Quantum Key Distribution End-to-End Service. If you can move to the next slide, please. So a bit of history here, and why are we speaking about quantum? So back in 1994, a professor from MIT developed an algorithm, Shor's algorithm, that aimed to be used for the future quantum computers. And this algorithm was designed to be able to factorize on a very rapidly large number. And this could be definitely problematic for the current security aspect and cybersecurity we are using today, because most of the cryptographic system relies on symmetric and asymmetric keys, and Shor's algorithm using quantum computing will be able to break asymmetric keys, so public-private keys, within minutes or seconds. At that time, quantum computing was more on the theory. We know that today quantum computers exist. Google claimed quantum supremacy, meaning that quantum computers are a reality. And implementing Shor's algorithm will definitely weaken the existing security and in the networks, providing decryption of the keys. Next slide, please. So there are several ways to provide countermeasures to these threats. And one of these countermeasures is basically using quantum property of physics property of the quantum theory to protect and to design a system that is able to distribute keys without being affected by the threat of the quantum computer. So to do this, the term is used for this is called quantum key distribution. So the principle consists of generating keys that will be distributed to two sites, two users, and those keys will be unbreakable by the quantum computers. This principle exists today, and it's already implemented in some of the terrestrial networks, but it has a limitation in terms of distance. It's going through fiber optics, and after 150 to 100 kilometers, due to the attenuation of the fiber, you cannot basically process further. And this is why we are currently developing a system that will distribute the keys via satellite. Could you move to the next slide, please? So within SES, we are working since 2018 in designing a system that will be based on a LEO satellite, and that will implement what is called a quantum protocol BB84, prepare and measure, which consists of generating quantum keys on board of a satellite and distribute those key materials to two sites. By the nature, the keys will be protected, and the randomness of the key material, which is really the essence of that enables a secure system, will be generated on board of our satellite. The system has been designed not only to demonstrate technologies, but really is designed really to provide an end-to-end service. That's really what matters us as a satellite operators, to be able to deliver to our customers an end-to-end service that will protect their cryptographic system. The principle of the quantum key distribution relies on optical communication. So there is an optical terminal on board of the satellite, and as well on the space gateways on the ground, to be able to receive the laser signal that carries the quantum keys. Next slide, please. So as I told you, we started the project in 2018 by developing the technology with our European partners. This program runs through ESA, so the European Space Agency, and it aims really to design an end-to-end system for QKD, proof of concept, and building really the premises of the system on the ground, to be tested on the ground. This program will be followed by a next step, which is to bring the technology, to bring the service in a real case environment. And we aim to launch a first satellite by 2024 that will be an in-orbit validation of the system. And again, this in-orbit validation system will not be only to validate the technology, but it aims to validate the entire chain, meaning the space segment, the ground segment, and the user segment. So bringing the keys up to the last mile to the user to really validate the system. This project falls into a European flagship program called EuroQCI. And the idea here is to also open the first demonstration to European member states, to be able to test the system, but also to integrate their own infrastructure into the network, the quantum network. As I mentioned, this program is running through an ESA framework, and it brings we bring with us European partners that provide unique capabilities to the system. Next slide, please. This system, so what we call EagleOne, which will be the in-orbit validation demonstration mission, will enable member states to connect to it. And here is an example of Luxembourg. So Luxembourg is defining currently its national quantum communication infrastructure. And as part of the program, the satellite component plays a key role. It's obvious that at national level, fiber optics might be sufficient. However, as soon as you want to connect distant places above 200 kilometers, you will need to implement a different system. And we strongly believe that a space-based quantum key distribution is key to provide not only in Europe this infrastructure to distribute keys, but also worldwide. Can move to the next slide, please. So this gives you a bit the current landscape in Europe that provides the quantum communication infrastructure and where SES is currently engaged. So as I mentioned, Luxembourg, the first two lines are really the national programs that aims to define and build the national infrastructure for quantum. Our Quartz program, followed by the EagleOne, the in-orbit demonstration that we are currently running. ESA is in charge of developing the technology through the SAGA program, and European Commission has taken the lead in the ground part. So the definition of the terrestrial quantum communication infrastructure. It is very important to mention that both terrestrial and space has to be together to enable long distance key exchange. Next slide, please. No. That's it. So again, thanks for listening. And if you have any question, please feel free to send your question via chat. Thanks.
Thank you, Thierry. Fascinating again to see how something which looked so far away in the future, actually a little bit sci-fi, like quantum, becomes a reality. And I actually have some questions for you about, concretely when all of this is going to become an actual reality on board our systems. But before we going there, I'd like to first thank our speakers for these presentations and repeat again that anyone is invited to raise any question on the chat. No stupid question. That can be very basic. If something isn't clear, if we already said, we can repeat. That's not the problem. We're here to precisely make sure that these essential elements of our innovation are well understood. So let me start maybe with one question for Stewart. You talked about adaptive resource control, ARC. I think this is, for a Spectrum conference, something which is really important to look at and talk about a little bit. Which frequency bands are we talking about here? And how much spectrum can this system provide flexibility and visibility over?
Yeah, that's a good question. So ARC is a software system, so it's completely independent of Spectrum. It just happens that the first utilization of ARC will be Ka band, because A3B Empire is Ka band. We're also going to be using on SES 17, which also has a digitized payload, but maybe less flexibility than Empire, and it has some relatively limited but very specific tasks to do on 17. But the point being that once you've started solving those resource management problems within software, it can be applied to any spectrum. And we're certainly talking to customers about reutilizing ARC as a product itself, potentially for other people's systems where it makes sense, and acting as a federation, if you will, to bring other systems together, so a customer can look across different systems utilizing the ARC component. At the end of the day, it's a series of sophisticated algorithms and the ability to interface with various components that manage those resources. One of the reasons that we're working with MIT is that we know, based on the flexibility of the systems that we're deploying, including A3B Empire, if you want to fully utilize that flexibility, at some point you have to bring artificial intelligence into the algorithm definition. It's just too complex. We won't do that out of the box, but we're certainly already working on that possibility down the road. Hopefully that's answered the question.
Yes, very much so. And actually that leads me naturally to the following question to Brian. Since you're talking about spectrum agility, it's initially targeted at Ka band, but how easy or difficult will it be to address all the bands, and what are the challenges on the design of the antenna?
Right, yeah. So that's right. So the product we are launching next year is focused on the Ka frequency band. And by the way, that product will cover the full commercial and military frequency range within a single product, and be able to create beams across those different frequencies simultaneously. And then scaling to other frequencies is relatively easy for us, because it's the same kind of functionality that we're getting out of this transformational optics technology, with the scaling relative to the frequency that you're trying to operate in. And many of the components that we are kind of designing on the back end under the lens, we are designing for both Ku and Ka frequency bands. And so as you saw in some of the pictures there, we've actually already created Ku prototypes. And that is certainly in our roadmap, as well as once we launch this Ka product, to shift to the Ku.
That's very good. And hopefully, this kind of solution will progressively develop in the market and progressively replace the legacy systems. We have a question to you from the floor, from Samsung. Rakesh Mehrotra asked how many satellites you can actually track simultaneously, and the type of antennas being used for this system.
Sure. Yeah. So the upper limit of how many satellites you can track really is probably way higher than anyone will actually ever use, because again, simply we have all of that kind of functionality in terms of the hardware sitting there within this terminal, and simply all you need to do in software is turn on those additional beams for every new satellite that you want to connect to. So I think most on the commercial side, having about 3 beams covers most of the use cases of doing make before byte handovers and multi-service connectivity and stuff. On the government side, there's some advanced features and services that they'll want to use that might utilize more beams than that. But really, for us, there really isn't a hard upper limit. It's we can support the number of beams that are required for that specific customer. And then, so the second part of that question was the types of antennas used. So in terms of the types of antennas that we can support on the satellite side, it's really any antenna, legacy systems or the new upcoming systems. But the satellite that antenna that we are using within the terminal is this kind of new transformational optics technology that I described that essentially uses RF lenses with some custom circuitry and feeds below it. So unfortunately, it's hard to go into too much more detail and explanation of how that works. I know it's something totally new, so it's kind of hard to describe quickly like this. But feel free to reach out and I can give a little bit more context of how that antenna technology works.
Yeah, fully understood, Brian. Indeed, it looks like 5 years of development. Well, not too much to change the paradigm. Stewart raised in his presentation many elements related to how we innovate with digital processing, flexibility, software design systems in our space segment. And Stewart raised the importance of security. Thierry precisely has explained to us that security is at the core of our concerns. We really want to make sure that the future systems will offer that degree of integrity, security of networks. We hear so much about security breaches nowadays in our communications networks. So Thierry, you made very clear that SES is leading a lot of efforts at European level and also at national level on quantum, on QKD especially. Now, practically, if that is an easy question to answer, I'm not sure, but how soon can we imagine that something will be implemented with QKD?
Yeah, so that's a good question. As I mentioned, I mean, the goal is really for the moment to have a in-orbit validation satellite by 2024. Obviously, the goal of this satellite is a demonstration, so it's not purely commercial. However, we have the idea of bringing also from that demonstration early customers, could be from institution, government, but also private market. And that's really the aim of the service, because it concerns really everybody, and with a commercial service couple of years after that, when we have all the certainties that the technology is really fitting the user requirements and answer all the security certification concerns. Because when you touch the cyber security, an important point is that you have a system which is recognized and certified.
Exactly. I think that's precisely the point. And I can imagine that, the certification, the standardization of all specifics and features of network systems in Europe is so essential, notably with the work done by SENS and ELEC and ETSI. We will, at some point, I guess, see that these bodies will be engaged into that, right?
Absolutely.
Yeah. Another question for you, Thierry. You mentioned member state support for the project, member state of the European Union. After all, this is a Spectrum conference on Europe, although we have a lot of people from everywhere in the world. So will this concept be also available for commercial customers to the future? So more specifically, how soon can we imagine that different satellite companies and our customers, our partners, will be effectively able to use this?
Yeah. So yeah, as I can confirm that the ambition here is really to serve the entire market. It's not limited to very specific users. Obviously, as you can imagine, there are always different components. Being from if you target the institutions, the defense sector, and private sector, you might have some segregation that you will have to apply on the concept. However, the service, as I mentioned, the end-to-end service, that we are currently developing, will address as well the commercial market.
Right, absolutely. Okay, I'm not sure we have other questions now from the floor. What I would like to suggest is maybe let's do a first tour of the different speakers. Maybe one of you have a questions for another. Opening the floor. Brian, any question maybe to Stewart or to Thierry about what they say and presented?
None that I can think of at this time.
No. Thierry, maybe you heard something from Stewart and Brian that raised a doubt or confirmed something.
Well, it's not easy. I mean, we are quite, I mean, we know a bit also what is going on the Empower and on the Isotropic. So, yeah.
You have already the answers.
Cecil, I've got a question for Brian. Can you talk a little bit, since you're the product guy, what are the market segments where you think you're going to get most traction, and are there market segments that we may not be thinking about as an obvious use that you're interested in?
Yeah, that's a good question, and a fairly probably a long question to answer with a couple minutes we have left. But maybe let's focus on the key aspects first. So, I think from a starting point, really this is unlocking a whole bunch of really advanced features and capabilities that have never been available from terminals before, and of course that's going to be extremely useful for government customers, definitely as a starting point and as early adopters to new technology as well, right? So for them, this is unlocking things like resiliency by using link diversity, by being able to use multi-orbit simultaneously, giving them redundancy to have multiple simultaneous links up at the same time for the type of data, and especially when you pair that, with the security features and the flexibility that Empower is going to offer them, I think is going to be an incredibly powerful solution on the government side, and that's both for fixed and mobility applications. By the way, one thing I didn't mention is we are, of course, since it is electronically scanning, it can scan very, very rapidly. So even things like off-road vehicles, it can track while it's doing all of that bouncing and everything off-road. We do have some really, really unique ways, and again, it's hard to describe so quickly, but trades within the terminal to essentially add or strip out hardware and functionality as required, to then create different products targeted at the other market segments, like commercial fix, so things like cell backhaul, for example. And we have some actually really unique ways to get some very, very interesting price points out of that, when paired specifically with the SES systems like Empower. And then we have a whole slew of other kind of product derivatives that we have out of that will address other various commercial and government markets as well. So I know that was the fast version.
No. It's good to hear, and obviously I've got a little bit of background in what you're doing. But how do you see the landscape for what are poorly called flat panel antennas, but non-mechanical, electronically steered? There are a lot of players coming in, different technologies. There's clearly in some segments enormous amounts of money being put into the development. But how do you see it developing, and your place in that over time?
Yeah, I mean, look, I think there's always going to be a certain place for parabolics, right? I mean, sometimes there isn't beating just taking a big physical thing and pointing it right at the satellite. But I think we are, with this technology, kind of overcoming that first hurdle where what people typically think of these ESAs and flat panels is that they aren't as efficient as those parabolics because they're flat and they have to do electronic scanning. But one of the unique aspects of this transformational optics technology is we actually have a little bit of extra volume in those lenses to shape and form and push the beam out towards the horizon. And so not only do we get really, really excellent scan range from a flat configuration, but our performance is very, very consistent and very flat out to those extreme scan ranges. It almost looks like a parabolic all the way out to very far scan ranges. So I think that's kind of the first hurdle of now you can have this flat panel ESA technology, but get that consistent performance like parabolic. So I think we'll be able to kind of share some of those markets more so than you've seen from other flat panel technologies. But I don't think we're ever going to see parabolics go away. I'll tell you that.
I hope not. We're buying quite a lot.
Yes,
but I really do want to see your product come to market. Yeah.
Very good. So I think we had an excellent session. Let us conclude. Maybe one word from the speakers. If I'm asking you, how do you see the market, and maybe one particular market segment in 5 years from now? Talking about new generation of antenna, talking about multi-orbit constellation, or talking about quantum technology being enforced in 5 years. Do you have one particular segment, one type of service, or one type of customers in mind which will obviously use our product? Stewart.
Yeah, I'll go first. I think what you're starting to see more and more is the move to software-based definition, digitization. You're seeing it at the satellite level. There's a lot of work being done on digitization of the Earth station, if you will, or whatever the terminal equivalent is. All of that means is a lot of flexibility, a lot of agility. And I would throw a question back to the spectrum at Broad, because this is a spectrum conference. How do the people in the audience think that the regulatory regime is going to be able to fully work with that flexibility that we're bringing to market and the technology? Because I think we are now starting to butt up against the systems are capable of doing a lot, but the regulatory regime doesn't support it. And with people taking chunks of spectrum away from satellite operators, and we need to think that through and make sure that we're in as robust a position as possible. We're a very small part of the overall telecoms community, business, revenue, but a very, very important part. We're not going to go away, so we need to figure that out, I think, going forward.
Very important point, indeed. Yes, Brian.
Sure. Yeah. Boy, incredibly hard to boil that down just to a specific customer and market, because I think when you pair kind of our terminal capabilities with the flexibility of something like Empower, you're not only going to be expanding kind of the possibilities for users like government, for example, where if you look at every modernization plan, they do want this multi-orbit, multi-satellite resiliency with flexible payloads on the satellite side and being able to route their traffic to different endpoints simultaneously. But then all the way down in kind of this really kind of cost-sensitive remote cell backhaul at enterprise customers, we now have this fully integrated terminal that is very, very easy to bring out to remote locations, very easy and inexpensive to install, and then have very low maintenance to lower the total cost of ownership. So now the economics at the endpoint have really changed here, and I think we're going to be seeing an expansion in a lot of new kind of more price-sensitive markets as well. So it really spans the gamut. It's hard to narrow down on one specific customer.
Very exciting. Thierry?
Yeah, I see really a lot of momentum in the GovSatcom and quantum domain, especially in Europe. So I really believe that communication, flexible communication, multi-orbit, multi-frequencies, especially for critical infrastructure and critical application in the what we call the GNI, so government and institutions. Will develop and will be the first market really to take advantage both in the communication area and the security aspect of the communication.
Yep, understood. Well, Thierry, Brian, Stewart, many thanks for your time and also for sharing your beautiful views and excellent products with the audience. And now it's time to give the floor back to Forum Europe. Thank you.
Thank you.
Thank you.
Thank you.